The next topic we're going to cover is how to apply ReentrantLock in practice to a non-trivial program. And the example we're going to use here is actually pretty cool because it comes straight out of the Java concurrency libraries. This is something that's part of the Java util concurrent package, and it's called the ArrayBlockingQueue, which is a bounded blocking FIFO queue. And all that means is that it stores things in first in, first out order. It will be blocking. So if the array blocking queue is empty and you try to take something from it, it'll block. If the array blocking queue is full and you try to put something in it, it'll block. And it's bounded, meaning that there's only n items that are allowed in the queue at any given time. So you can see here that array blocking queue is a class that extends something called abstract queue, and that factors out some common code that's used by other implementations of blocking queues like linked blocking queue, for example. And it implements the blocking queue interface, which defines a whole bunch of methods, most importantly for our purposes, take and put. We're going to look both at the interface of array blocking queue, in other words, its API, as well as its implementation in a few key places. Now, the way this works under the hood is the array blocking queue uses a Java ReentrantLock, as well as some other stuff that we'll talk about later. And it doesn't use, it intentionally does not use Java built-in monitor objects due to the limitations of built-in monitor objects that we've talked about. Like you can't do blocking operations, and there's other limitations as well. You can't do non-blocking operations. You can't interrupt things and so on. Now, this ReentrantLock is needed to protect the state that makes up the object's implementation. And that state, as you can see here, includes an array, a fixed size array of items, because it's a bounded blocking queue, so there's a fixed number of items. It also has some fields to keep track of the next indices to take and put when you insert or you put and take elements in and out of the array blocking queue. And it also has another field that keeps track of the count of the number of elements in the queue. These fields are not defined as volatile because they're protected by the ReentrantLock. And if you recall, ReentrantLock also has the property of updating caches to ensure atomicity, visibility, and also ordering. So much like the atomic operations we talked about before, these things do actually double duty. They protect regions of code, and they also ensure that caches are properly flushed. Okay, so let's take a look at how we might use this. So over here, you can see that we're going to make a new array blocking queue of up to 10 items. And I'm going to show you the code on the right-hand part of the screen, and I'm going to kind of visualize it on the left-hand side of the screen. So we've got array blocking queue that has a bunch of methods that operate as critical sections. We're going to show a little use case here. Some thread, let's call it thread T1, comes along, and it wants to take the item out of the queue. And for sake of argument, we'll say that the queue starts out empty. It can hold up to 10 items, but it does not have any items in it at the moment. So take is going to block. So when we call take, that's going to acquire the lock and enter the critical section because nobody else owns the lock. And that's going to happen when the lock interruptibly method is called. So if you were to take a look at the take method implementation, you would see the first thing it does is it stashes away the lock into a local variable, and then it says lock.lock interruptibly, and that will increment the hold count by 1. There is nobody else there, so we get exclusive access to it. We are now the owner and the holder of this lock with a count of 1. For sake of argument, let's now say another thread comes along, thread T2, and it also tries to take something out of the array blocking queue. And what will happen in this case is because we already have thread T1 owning the lock, thread T2 is going to have to block until thread T1 is finished doing its thing in the critical section of take. So this will basically park itself to run later. So at some point when thread T1 is finished successfully taking an item out of the lock, and I won't cover that logic in detail until we get to condition objects a little bit later. What happens here is when it's all done and it's finally got an item, one item has shown up, then on its way out, it's going to go ahead and unlock the lock in the finally portion of the try finally block. Again, always use try finally just to get in the habit of making your code safe from either existing or future exceptions that could be thrown. What will happen here is unlock will decrement the count by 1. That'll go to 0. And then that causes the underlying ReentrantLock mechanism to release the lock and make it available for other threads like thread T2. So again, we always use finally, just a good habit to get into. And now that we've unlocked the lock, thread T2 can wake up and enter its critical section and start to do its thing. And its thing will look pretty much like what we just showed for thread T1. Now, what actually happens under the hood, I've kind of skipped over a very important part here, is that there's some conditions or a condition that's being checked in a loop inside of take. And what happens here is while the number of elements in the array blocking queue is 0, we're going to call the await method on a condition called the not empty condition. So the way to read this is basically to say, essentially, sleep until count is greater than 0. And we'll talk about that in more detail when we talk about Java condition objects. I don't want to get too far ahead of myself at this point, but just be aware that that's the basic brains of this whole thing. We're focusing on the ReentrantLock part. And ReentrantLock is always used in conjunction with a condition, or maybe a better way to say it is a condition is always used in conjunction with a lock. And that's to ensure that the checking of count equals 0, or whatever the condition may be, is done with the lock held. So we don't have to worry about race conditions or corruption of shared mutable state, because count is shared between multiple threads. This particular way of doing things, by using the lock acquisition and then this little check with a while loop, that's called the guarded suspension pattern. And you can read more about that at the Wikipedia link at the bottom. And then the whole way of doing this thing is called the monitor object pattern. And you can read about that in my POSIT 2 book or at the link at the bottom of the slide, because I wrote a paper on this many years ago. And you should think about guarded suspension as kind of Gandalf standing at the bridge of Khazak Doom, telling the servant of Morgoth, the Balrog, "You shall not pass." And basically what he's saying, or what we're doing here, is we're not letting things pass until the condition is to our liking. By the way, I just happened to watch that scene last night on YouTube, and it's an amazing scene for so many different reasons. But if you haven't watched the movie in a while, you should go back and Google, Gandalf fights the Balrog, and you'll see it. It's really cool. Okay, so that's the end of our example application of ReentrantLock, applying a ReentrantLock to a portion of the array blocking queue class from the Java util concurrent package. As I mentioned, we'll come back later when we talk about condition objects and really go into this in more detail and talk about how condition objects are used to allow multiple threads to coordinate amongst themselves in order to be able to implement the array blocking queue semantics for taking and putting.